Welcome to the Knowledge Graph seminar. Our theme for this week is how to design the schema of a knowledge graph. We are fortunate to have with us today two outstanding talks on this topic. The first of which will be given by Dr. Peter Patel Schneider, who has been involved in the design of two very prominent ontology languages, including OWL. The second presentation will be given by Andra Wagmeister and Professor Jose Gallo, who will be telling us about how they extended the schema of the Wikidata knowledge graph with COVID information. So these should be really fascinating talks. So without much further delay, I hand it over to Peter. Peter, over to you.
Okay, and unfortunately, I can't seem to share my stuff, so I'll have to do remote control and ask for movement on the slides. So anyway, so this talk impinges on schema design, but it's sort of on what's missing in schema design in knowledge graphs. And so the idea is that, next slide, please. Right, so the problem with that I see in knowledge graphs is that there really isn't knowledge in them, just data. And so this talk is about how we can get to knowledge from data. Next slide, please. So to support that thesis, I need to do two things, I think. One is to convince you that there's more to knowledge than just knowledge graphs, and then how to add that missing bit. And I'm going to use Wikidata as my example knowledge graph because it's there, because it's accessible, because it's nice. Wikidata is a bit different from the knowledge graphs, but not so much different, at least not for the purposes of this discussion. I am being a bit harsh on Wikidata. There are things in Wikidata that I'm not going to talk about that help with organization a little bit. And Wikidata is a community effort, which makes things very hard to do in Wikidata. So in some sense, they're trying, but perhaps not the way I would like them to do. Next slide, please. So what is Wikidata? Well, I don't know how many of you are aware of it, but it's a very large community-driven repository with about over 93 million entities, and including all sorts of things. It's something that anybody can update. You can just go to the Wikidata site, which is wikidata.org, pull up a page and edit it. There is a graphical editor. Your edits are done in real time. Like Wikipedia, people get angry at you if you make stupid edits. Like Wikipedia, you should log in so that people know who you are when you make the edits. But you don't have to. You can make any edit you want. And the data in Wikidata is absolutely free, CC0. You can take it, you can use it for your own, you can do anything with it. Next slide, please. So here's an example of the display interface for Wikidata. You can see a Wikidata page, looks a lot like Wikipedia. This is Elizabeth Taylor. There's lots of information about Elizabeth Taylor. I just put the top bit on. Behind this page is essentially a database of all of the information that Wikidata has about Elizabeth Taylor. You can actually get that. You can see it in a dump. You can do lots of other things. But this is sort of the visual interface you get to see. Next slide, please. There also is a query interface for Wikidata that is done using a Sparkle query interface and a translation from Wikidata to RDF. Here is the Wikidata query for the children of Elizabeth Taylor. And if you can actually read the text in that query box in the top right, you will see it's very obnoxious to use because Wikidata inside uses numeric identifiers and the query interface requires you to use them. So here we've asked for the children of Elizabeth Taylor, and there's 4. We can see them down the bottom. We can see their identifiers on the left, and they're essentially names or labels on the right-hand side. Next slide, please. So is Wikidata useful? I claim absolutely. It's large and growing. So currently 1.3 billion facts or so. Facts that's perhaps a little bit of an overestimate because some of the facts are kind of internal things. Next slide, please. It's high quality, includes lots of information. It's hard to convince you just in one example, but here we have the children of Elizabeth Taylor, and it includes both her natural children and her adopted daughter. So people have gone to fair bit of effort to include lots of information and to do a pretty good job of making sure it's correct. Next slide, please. Another very nice thing about Wikidata is it has many, many connections to other repositories. Each chunk here is a link to Elizabeth Taylor and some other place, such as the VIAF site, so an ISNI, lots and lots of things. So Elizabeth Taylor has dozens of these. So it's a very, very useful as a central repository for the central place for the semantic web, because you can then get to lots of other places. Next slide, please. So then, I haven't shown you a graph quite yet. So you might think, well, Wikidata is just a database, but it really is a graph. You can look at it. It has nodes in it. It's got edges. It's got labeled edges. You can actually display parts of this graph. Here is a graph of the descendants of John Powell Taylor, who I picked because he's a great, great grandparent of Elizabeth Taylor. So you can see Elizabeth Taylor, although the name's hard to see, but you can get out graph information from Wikidata. It's a graph. Next slide, please. It has information about the real world. It's another aspect of being a knowledge graph. Not just people, but places, lots and lots of things that are about the real world. And the information is close to truth in the real world. Next slide, please. It also has quite a large schema. So here we have the definition of human, and we can see down, you can't see much of it. The most interesting part of this thing is you look down to the bottom right, you'll see it is a subclass of another class called person. Next slide, please. So here is the person class. Okay, next slide, please. It has definitions of properties or relations. The name, I can never keep straight which system uses relation and which system uses property. I think Wikidata uses property. So here's the definition of the property spouse, okay? So spouse is a relationship, and it goes from entities in Wikidata to other entities. That's what the data type item on the bottom is. Next slide, please. Here's a definition of child. Next slide, please. Here is lest you think that this is a small ontology, here are the generalizations of human. So human is a subclass of person, which is a subclass of individual, which is a subclass of individual entity, which is a subclass of entity. So we have a fairly large class hierarchy above human that goes up to the most general class entity. Next slide, please. Underneath human, we have very, very many specializations of it. Where did these come from? Well, Wikidata has essentially an item for each page in Wikipedia and has grabbed many of the links from Wikipedia. So many of these classes, these subclasses of human, come from Wikipedia, but others come from other places. So it's a graph. It talks about the real world, and it has classes and relations. That's enough to make it a knowledge graph in my view. Next slide, please. Next slide, please. But does Wikidata have knowledge? How can it not? You've seen lots of stuff there that looks like it's knowledge. Well, next slide, please. Appearances are kind of deceiving. So in Wikidata, we have this ontology or taxonomy, whatever you want to call it, with individuals that are instances of classes. And if we ask about the instances of human, and that's Q5, and instance of is P31, if you can actually see that, the stuff in the query. how many humans are there in Wikidata? We can run this query in the query interface and we get 9,067,016 as of, I think it was yesterday when I ran this query. But is that the right answer? Next slide, please. No, it's not the right answer. The problem is that there are instances of subclasses of humans in Wikidata, and those don't get counted when you do a direct query on instance. You need to also explicitly count the instances of the subclasses of human, and not only just the direct subclasses, but also all the transitive subclasses underneath it. So to get at the real information, the stuff that you should be getting from Wikidata, you have to carefully craft your queries. So instance of and subclass is so important that anybody who knows much about Wikidata knows that you need to put this little P31/P279 star in your Sparkle query to get instances of a class. But the similar problem affects properties, not nearly to the same extent though, and people routinely forget to look at that. Even worse, under some circumstances, even the query here is insufficient to get all of the instances of human. In a sense, there is some implicit information that tells you what Wikidata is supposed to mean, but that's not machine readable at all. It's in the definition of Wikidata, which is text, or it's in other places. Next slide, please. So here's another example of where information is only available outside of machine readable stuff. So here's a definition of woman. It says right there, woman, female, adult, human. All right. How many women do you think there are in Wikidata? Next slide, please. 0. But, oh, we forgot. We also need to look at subclasses. Next slide, please. 11. 11 instances of woman in Wikipedia. At one time, when I did this a few years ago, there were actually 42. Now, so that's maybe going in the wrong direction, but neither 42 nor 11 are the right answer. Apologies to Douglas Adams. So what's happened here? Well, we have this class woman, and it's got a perfectly good natural language definition, but there's nothing in Wikidata that takes the instances of human that should belong to this class and makes them belong to this class. In other words, there's no recognition conditions. So if we wanted to figure out what are the women in Wikidata, we would have to, instead of asking the easy question, we would have to figure out a query that is equivalent to the natural language definition, natural language description for women. Next slide, please. Actually, here's the 11 of them. It's another problem with Wikidata. We see that some of these are women of some sense, and some of these are kind of titles. So what is it? Oh, Queen Consort of Greece. There isn't any at the moment, but that is actually a kind of a description of a bunch of women. It's not an actual woman, historical woman. Next slide, please. So another problem with getting information out of Wikidata is that there's lots of information in Wikidata that gives you a context. And if we ignore that context, we just get the wrong answers. So here we're asking, who are the spouses of Elizabeth Taylor? Well, Elizabeth Taylor's dead? I think so. Anyway, she does not have 6 spouses at the moment. She has either 0 or 1. She must be dead. Anyway, 6 is the wrong answer, right? If we're asking who are the spouses of Elizabeth Taylor now. If we were asking who are the spouses of Elizabeth Taylor at any time, yeah, then I guess it would be the right answer. But that's not the question that people tend to ask. They want to know what's true now, what's true at some time in the past, what's true in some other sort of context. And that would be okay if we knew exactly how to construct that context if a machine could figure out how to construct that context. Next slide, please. But the problem is, there's nowhere does it state in machine readable form in Wikidata where do we get the context that we need. So what happens in Wikidata, we have these facts, and here are some of them. So these are some of the spouses of Elizabeth Taylor. So Richard Burton was a spouse of Elizabeth Taylor from the 15th of March 1964 to the 26th of June 1974. That was their second marriage. Oh, right, there's both of them are right there. And then again from 75 to 76. Right. To figure out who is the spouse of Elizabeth Taylor at some particular time, we need to look at the start time and end time information, which is associated with the facts in Wikidata. And the trouble is there's nothing really that tells us that start time and end time is the right associated information to get what's true at some particular point in time. At least there, again, so if I am a human and I can write the queries myself, I can carefully craft a query which gives the spouses of somebody at some particular time. But it won't give other kinds of information at that particular time because other kinds of information use other qualifiers to give their start and end date. Some of them can things like inception, time period active, a bunch of things like that. It's all over the map, and you don't know what you need to know before you can find out things out of Wikidata. Next slide, please. So another problem with Wikidata is that there's very few sanity checks. I showed you this one about the queen consorts of Greece, and I couldn't resist but putting in a non-Wikidata example. Here is the results of a Google query from a few years ago, which actually pull information out of a very early version of the Google Knowledge Graph. And we have the 6 wives of Henry VIII. And there's something wrong here, right? Not only is it wrong, it's ludicrously wrong. Somebody didn't, there's no check to say that a currently living actress is not suitable to be a wife of somebody who lived in the 16th, 15th century, somewhere, but quite some time ago. So it's understandable that there's mistakes in any knowledge graph. You just don't want them to be ludicrous mistakes like this one. Next slide, please. So there's something wrong with Wikidata. You don't really get what you want. Does this mean that it's not knowledge? I claim yes. And my thing that I point back to is this talk from Russell Ackoff, oh my goodness, 2 decades ago and a bit. And he says that knowledge is information organized and ready to put to use. And Wikidata isn't really quite ready to put to use because you have to know stuff before you can figure out the right way to get the information out. Next slide, please. So to reiterate, using Wikidata requires knowledge that's not in the data. Humans can often, sometimes, I use Wikidata a fair bit. I even get confused occasionally. But humans can generally muddle along. Programs can't unless some human goes through and either trains them, and how are you going to get the training information list, or writes some code that figures out exactly how to do the right thing. And there's no data to find. You just have to, bung it all in. So the information in Wikidata isn't really quite ready to use, and thus Wikidata doesn't truly have knowledge. Next slide, please. All right. So how do we turn Wikidata into wiki knowledge? So we really need to do something to add in the consequences of the data, if we know what they are, and that's the job of logic. So if we can design a logic for Wikipedia and implement it, we can figure out what the consequences are. We can take the language information and turn them into expressions in this logic. We can take context into account by figuring out how to combine the qualifiers. And then we can augment the query interfaces with the current context. I'm not going to consider this last one. That's the job of a sort of expanded query system that would have a background context. Next slide, please. So it turns out that there are logics that can be used for this purpose. I should, oh, I forgot. I should have actually put a good pointer to the source of Mars and Marple. Mars and Marple come from the group in Dresden headed by Marcus Krutsch. They are excellent logics. David Martin and I added a few minor things to make them a little bit better for Wikidata, hence the eMars and eMarple. But these are a family of logics for knowledge graphs. Their main idea is they augment regular logic with qualifiers on the facts. So these little extra things that provide start dates, end dates, they add like where somebody was married, lots of things. We also, these logics also add the data types from Wikidata. They add rules for handling the qualifiers and inferences, and they add constraints, which is another part of Wikidata. So 2 of these logics, Marple and eMarple, can actually be implemented using forward chaining rules, and the complexity of inference in them is not too bad if you make reasonable assumptions. And I'm being purposely very vague there. To get into the details of these logics would be an entire, well, at least an entire hour-long talk, and I don't have a chance of doing it here. Next slide, please. Yeah. So how do we then take this? So if we take eMarple and we take the facts from Wikidata, and here are a couple of them. So here we have instance of Elizabeth Taylor Human, as we've seen before. And now we have spouse of Elizabeth Taylor, Richard Burton, and this little @ sign is sort of the extra stuff that you add onto the fact. And here I put a start time, and there's a bunch of other things that from the slide a few slides ago. So essentially you take all of the facts in Wikidata and you pile them up and you make them into an eMarple knowledge base. Next slide, please. It's convenient to say that things like subclass and subproperty don't have context qualifiers, i.e. if human is a person, if human is a subclass of person, then it always is a subclass of person. This isn't absolutely necessary, but makes everything a lot easier. Next slide, please. We add then rules that define the consequences of the Wikidata ontology properties, i.e. this is what the Wikidata ontology is all about. And here we see that subclass is transitive, that instance of distributes over subclass, whatever that is, and that subproperty of is transitive. And we note that with these little x's there, we're dragging the context along. So if something is an instance of X and X is a subclass of Y, and that's only true at some particular context, then we drag all that information around. So that's for the superclass. Next slide, please. We then add in properties of domain properties. So here's an example. Spouse is a symmetric relationship in Wikidata. That's not automatically inferred for you in Wikidata. You can add a rule which does that for you. Next slide, please. We can actually add in constraints. I haven't talked about constraints at all. Constraints are things in Wikidata that says what kind of updates are perfectly fine and which ones are not very fine. So here's an example one. So essentially says that well, anyway, here's an example constraint from Wikidata, and it moves over into this logic quite nicely. Next slide, please. That was the easy part. Now for the 2 hard pieces. Next slide. So we have these qualifiers, and we really want to be able to combine them when we do inferences. And we want to do things like, well, if we have 2 start times and want to combine them, we take the max or the later. And if we have 2 end times, or actually multiple end times, we want to combine them, we create the earlier. And this is how you can do this. So if you have multiple start times, so the start time of a result is the maximum of the start times of the components of an inference. And similarly, next slide, please. This is a difficult process because the qualifiers are an important part of Wikidata, but the English language descriptions are quite vague. It's unclear as exactly what these things mean and how they should be combined. So there's quite a bit of work that would be need to go in to figure out what these things actually mean, particularly when you get multiple combinations. Next slide, please. And then the other thing is we want to do things like woman. And here's an example actually for female human. We want to say that if something is a human and their sex or gender is female, then they're a female human. That sounds pretty reasonable and pretty easy to do. Next slide, please. The problem is that there are many, many, many such classes. I haven't counted them, but my guess would be at least tens of thousands, probably hundreds of thousands. Well, no, I take that back, tens of thousands. Some of them may not have good recognition conditions. You don't really know what it takes to belong to some oddball class, so you need to make some guesses. Next slide, please. So with all of that, we can then turn Wikidata into a knowledge base in a logic. We can then say, okay, what Wikidata is the consequences in this logic. But of course, our problem is that's not enough. We actually have to implement these things. And so far, the stuff I've described is so far just a proposal. It's close to being realized in some systems, but there's nothing exactly that does it. So there are implementations of property graphs that can store Wikidata statements. Some graph databases have rules that are very similar to these, e.g. GraphDB, but no system actually implements these rules as described above. Considerable work will be required to implement the logic here. I would be perfectly happy to do it if somebody would pay me to do it, but it's just, there doesn't seem to be anybody who's too interested in this. But in the end, it's all just forward chaining rules. And one thing you could do is implement this logic by essentially encoding everything in RDF and using an RDF rule engine, and there's quite a few of those. Next slide, please. A bigger problem in this process of turning Wikidata into Wikiknowledge is the Wikidata community, in my opinion. It's quite fragmented. Portions of the Wikidata community are not friendly to this kind of effort. They don't see a need even for an ontology. It's very difficult to see how enough convincing could be done to get enough people in Wikidata to go along with this vision so that it could be actually done in Wikidata. And part of the problem, of course, is that the support group for Wikidata, which is part of Wikimedia Deutschland, is very resource constrained. They don't want to do any programming. They only want to take things off the shelf. Even for very simple changes, they're unwilling to do even simple changes to open source projects. So I think the biggest problem with getting a vision like this done is actually getting a community to push for it. So what do we have? We have a proposal for a logic that turns Wikidata into Wikiknowledge. We have some problems with implementation. We have some problems with the status in the community. Next slide. And that's it. So in summary, Wikidata is a useful knowledge graph. And my claim is, like other knowledge graphs, Wiki doesn't quite qualify as providing knowledge, but you can do it, right? As I've tried to describe, you need this implementation is required. The computational aspects are not horrible. It's a forward chaining rule system. It could run over the data. Wikidata already has lots of little bots that run over the data already, so it's not a significantly more computational effort. And the benefit is computer consumers, and actually by which I really do mean computer consumers, see knowledge. There's much less pain in building programs that actually get to see the knowledge that's inherent in Wikidata. So let me, in concluding remarks, say, how does this have to do with defining schemas? Well, in my view, a schema is much more than a taxonomy. It's much more than just saying that human is a subclass of person. It's really giving things like these defining conditions for woman or female or butcher or baker. As a matter of fact, butcher and baker are also problems in Wikidata. If you want to know the butchers in Wikidata, presumably has 0 butchers, but there's lots of butchers described in Wikidata. You just can't get them by getting instances of the class butcher. So in my view, to make a real schema for a knowledge graph, you have to have something more than what exists in current knowledge graphs. And to do that, you need to have a logic which at least has some form of recognition conditions and some form of inference that keeps everything on the up and up so that you don't get these false views of what actually is in your knowledge graph. And that's it. Thank you.
Thank you, Peter. That was an excellent presentation. We will take the questions at the end. We will just move right along to our second presentation. Jose or Andra, do you guys want to share your slides? Yes. So I'll let you guys take it from here.
So let me start by saying thank you for the opportunity to talk a bit about our work and specifically of adding COVID information to Wikidata. I'm doing this presentation jointly with Jose Labra, and I will personally present the use case, and Jose will dive in more in the shape expressions, which we will discuss. I would also like to thank Peter for setting the stage there, for giving a very well description of Wikidata. But let's start. So the reason for this, we recently published a paper,
Andra, please feel free to turn your video on if you like. You don't have to, but
sure. Oops. Okay. I need to give me a second. So
yeah, we can see you now.
Yeah. Can you still see my screen? Yes, I guess so. So present. So this talk is the use case that we're going to discuss is a protocol that we recently published to adding data to Wikidata, and specifically how to align resources in regarding human coronaviruses on Wikidata. The opportunity was, of course, the current ongoing pandemic, but the intention of the paper was also to create a protocol or of steps that can be used to align resources. Why do we want to do that? Well, here you see, for example, the number of papers, and I just randomly picked the graph, some topics. So I took Ebola, which you see can spike in 2014. This is citations in PubMed. It's a very nice service that is online. So you see that you have Ebola, there is malaria that spiked in the just after World War II and then gets into a plateau. Here we have the HIV and we have AIDS, and then suddenly we see here COVID-19 and SARS-CoV. So we are presented with a spike of knowledge and scientific papers ongoing, and how to make sense of everything that's coming out. There is also the risk of getting erroneous content that gets out or that gets rejected in the process. So how can we find out back to the resources? How can we find out what is true and what is not true? Or can we get back to the data that substantiate all the claims that are being made in the literature? So early on in March 19th, I saw a tweet that this tweet started the writing process of this paper. And this is a tweet by Egon Willig Haskin, who I asked Andra if their bot can be used to do this instead. So what are being discussed in this tweet thread is trying to add genetic information about the SARS-CoV-2 virus onto Wikidata. What is Egon talking about? So when he said if we can use the bot. He is referring to the GeneWiki project. The GeneWiki project is a project that started in 2008 that aimed at creating a Wikipedia article for every human gene that exists. It captures data, structured data from various databases such as identifiers, and it captures summarized knowledge via crowdsourcing. So at the time, Wikipedia pages were created for every gene, but there is the limitation. This was only the English Wikipedia, and it was hard to get data back into structured formats. So in 2012, Wikidata emerged, and the GeneWiki project moved forward on putting the genetic information about genes, proteins, diseases, and drugs onto Wikidata instead of Wikipedia. Why Wikidata? So Wikidata is similar to Wikipedia in the sense that what Wikipedia is to text, Wikidata is to data. It uses similar infrastructure as Wikipedia. It's actually an extension to the MediaWiki framework that drives Wikipedia. It is completely free, and like Wikipedia, anybody can contribute. It covers all domains of knowledge, and it has extensive item history, talk pages, etc. It comes with a powerful query language, and also unimportant is that it's stable. It exceeds quite some funding cycles. So where research data often decays because of lack of funding, it can live on Wikidata. So with the emergence of Wikidata, the GeneWiki project switched from Wikipedia to Wikidata. And this is the current state of affairs. The GeneWiki project is maintaining a set of bots that is sourcing various public data sources on genes, compounds, proteins, literature, metabolic pathways, biological pathways, and are maintaining these resources on Wikidata and regularly checking those. So what does that entail? What it is that of a select sources of public databases, the first step is to do schema reconciliation. If you have a gene, how do you look for a gene? Peter already said you have the instance of. So if you want to talk about the gene and you want to align that, what are the statements or properties that you want to use in Wikidata? That's the first step of doing that. How do you identify that? When in the current time, you can go to looking at similar items. You check for a gene that already exists and just list the statements. You can go to wiki projects, which are dedicated projects by sub-communities within Wikidata on a specific topic, or you use a tool which Jose will discuss a bit later, which extracts the schema. And then once you have this schema set written, you write a bot that checks and updates data that exists in there, either on their labels, shared identifiers, or IRI mappings. So 2 days later, this tweet went out and says that we actually got the first schema for Wikidata on virus genes, and that looked a bit like this. So this is a machine-readable format called a shape expression that indicates that every virus gene should have some subclass information, and these are all properties that are in Wikidata. And with this, I would like to give the floor to Jose to dive a bit into the schema, into the shape expressions that we are describing here. Should I use the slides, or would you like to share, Jose?
Jose, we cannot hear you. You're probably muted.
Maybe can I try to share my screen, or?
Okay, I will stop then. Yes, you can.
Okay. Can you see it?
Yes.
Okay, so we're going to talk now about entity schemas and shape expressions at Wikidata. So this is the first why shape expressions? And why? Because we started with shape expressions, and then shape expressions were adopted in Wikidata. So first, what was the reason to create something like shape expressions? And here we are talking about knowledge graphs, and a lot of people relate also knowledge graphs with RDF. Because there are a lot of good things. I mean, RDF is very good for data integration because you can merge RDF graphs automatically. You also have the possibility to use RDF as the basis for knowledge representation, and also RDF is very flexible in the way that you can adapt RDF using URIs to different contexts. And I think RDF is reusable by default. And also there is a lot of tools that you have, the data stores and Sparkle endpoints, and you can even embed RDF in HTML. So there are several good things about RDF, but there are other parts that I think, I think RDF is not yet the preferred technology by web developers, for example, and I think there are several reasons. And one of the reasons that happens in practice is that when you try to consume and to produce RDF data in knowledge graphs or Sparkle endpoints, and usually it's not very easy because, for example, Sparkle endpoints, the documentation is not very good. If you are a consumer, you want to see what are the contents, how to do Sparkle queries, as Peter was saying, that usually is difficult. You need to look to the data. Sometimes the documentation is just a set of samples of Sparkle queries. So there is no a good documentation or a good description of the contents of a knowledge graph. So Invisible is difficult. And to solve that, in 2013, there was the proposal of defining a language which was called shape expressions, and the idea of that language that later was going to become there was another language which was shapes constraint language, which also takes the idea of a shape, is that the producers can describe the producers can, they know what are the contents that they will produce, and they can ensure that they want to produce those contents. They can also advertise and also document that structure, those shapes, and they can even generate user interfaces so to validate the data that people can enter by manually. Also, for consumers, it would be great to have some understanding of the contents behind those Sparkle endpoints, and to be able to validate the data before starting to process or to do something with that data, and also to be able to even generate queries or optimize Sparkle, some queries or even the data, so they can be optimized. So those are some of the reasons why shape expressions were created and were very useful. Just a very short introduction to shape expressions. It was defined as a language with two main goals. That one was to be human readable and also machine processable. Human readable in the sense that the intended audience is people who know, for example, Sparkle, but also they are not people that need to be programmers, so they can be domain experts. And in fact, for example, in the community of Wikidata, you can see people who are able to do Sparkle queries, and they are not people who have a lot of knowledge of computer science. They are just people in other domains that they just can do Sparkle. So the idea of shape expressions was to have that audience as the goal. So the syntax is inspired by Turtle and also by Sparkle. This is an example of a sex schema. We are saying that you have a user which has a name which is a string and knows another user. And also the language is machine processable in the sense that it has a formal semantics, also several open source implementations in JavaScript and so on. And I will talk a little bit about these online demos that I will show later. So just to finish this short introduction to shape expressions, imagine that you have some data. You have, this is RDF data in Turtle. Then you could have a schema, sex schema, trying to describe the contents of this data. In this case, it's a very simple example where you have a very simple network where you have Alice, which has the name, which is a string, and knows herself and Bob has only declared the name, which is Robert. And then finally we have the shape map. And the idea is that if you have these three things, then you can validate, and the validation will say, okay, so now I can, if I try to check if Alice is a user or conforms to the shape of a user, then I can go here as Alice must know Bob. In order to be a user, this one has also to be so the shape of Bob must be a user. So during the validation, there is this thing that you can say, okay, Alice was a user because Bob was also a user. So this is the result of the validation. So this is a very short introduction to the shape expressions language. It started in 2013, 2014, and it was available. If you want more details about the shape expressions, we wrote this book, which is called Validating RDF Data, and also the book is also available online. It's HTML, and there is also this tutorial that I gave last year to the International Semantic Web Conference, where you have also the slides and you can take more information about that. And now, what is the relationship between these shape expressions and Wikidata? Well, the thing is that in 2019, Wikidata adopted shape expressions as another namespace, which is they changed the name a little bit because they used entity schemas, but those entity schemas are represented using shape expressions, and now you have a new namespace. So there is the other namespaces. The most popular is probably the Q and a number is for entities, P is for properties, L for lexemes, S was reserved for senses. That's the reason that they don't use for schemas, but they took E for entity schemas. So for example, if you click here, this is the entity schema. Can you see it? So
Yes, we can see it.
Yes, okay. So this is the entity schema of an author, and this is in Wikidata. So there is E42 is entity schema of an author. So and maybe I can even do the sample to show how you can validate data. For example, this is the entity schema. There is, if you click on check entities, then it opens this tool that you can use to validate entities. For example, we can do a Sparkle query here. Let's see if it works. And you can check what are the entities to validate. It is resolving this Sparkle query, and now it starts to do the validation. I think some of them validate, and one, I mean, it is okay. So this is an example of what Peter was saying before. So you can have some data that satisfies or conforms to this shape expression, and maybe other data that is failing this shape expression. So this is something that I think is accepted in Wikidata because not all the data is correct, and there are things to repair. Okay, so that was the introduction to the shape expressions, and now I wanted to continue a little bit with some tools and use cases for shape expressions. The first one was to validate, and I think I already said about that, so not going to repeat, but say that something that you can do with this validation is also to filter entities, because you can filter those entities that conform from those entities that don't conform to some given schema. You can also, we created several tools that we are working. For example, this is a tool called Yassi, which allows you to edit shape expressions. And this is nice because, for example, if I go here to the E42, well, no, what anyone, you can see that you can have autocomplete, and so it is quite useful to edit shape expressions. There is also a visual editor for shape expressions. The RDF Shape is a tool, a playground for shape expressions, and Wikishape is a similar one but specialized for Wikidata. Then we also have the Sexer tool that was Andra saying is doing in the opposite, and this was interesting because when we started with shape expressions, I remember we went to the conference on Wikidata, and the users asked us if it was possible to extract from the RDF data that was already existing, to extract and to infer the shapes, so the schema. So we created this tool because it comes from the needs of the users. And another tool that the users are asking now is that if they can generate forms from shape expressions, because I mean, for example, if you know that you want to create an author and you know what are the properties of an author, you can create a form. And for example, let's see. For example, this one. This is a Cradle, and if it works. Here, for example, well, in this actor, for example, so from the shape expressions, it can generate a form that people could fill and so on. So this is something that the users, I mean, it's a practical application that users are asking. And finally, about shape expressions in Wikidata, something that was also very interesting is that the adoption has been increasing. People are starting to use more and more these entity schemas. There is now this schemas project, and also there is a directory of entity schemas. If we click here, you can see a lot of entity schemas for hospital, for hospitals. Again, some of them are repeated because, as you know, this is in the Wikipedia style of collaborative, the wiki style of collaborative things that people just add things and sometimes they overlap. So this is also an interesting thing, and so just and opens new challenges. For example, this collaborative work and the different views of what is correct and what is not correct. That's also very interesting. And this trade-off between the quality of the data but versus the freedom that anyone can add whatever he wants. Also, there are this collaboration between domain experts from different disciplines. So this was what I wanted to say, and now I think Andra can continue with the community. Yes. So I probably have to stop sharing. Are you there, Andra?
Yeah, I was
you're
muted.
muted.
Okay. I'm opening it again for sharing. So let's quickly go past the slides. Yes, I'm wrapping up. I think I have about 5 minutes or less. So this is what I'm going to do. So what we've done in going back to the COVID, adding coronavirus data on Wikidata. What I'm showing here is slides of what we've been doing in the GeneWiki project. And that is in the first step is where you engage with the community of domain expert and discuss how the data that are available in the world and with the public license, because that is something that needs to be emphasized as well. Wikidata is a public knowledge graph, so only public data can go in. And then what you do in this community engagement process is you're trying to get the extract relationships on a piece of paper. And once there is some consensus in there, this is also presented to the community at Wikidata at large, usually in discussion fora. But once that is in place, that schema is then transformed into a shape expression. In this case of Wikidata, that can be used for legislative review. It can be used for documentation, because this is a decision by a group of domain experts about how the schema should look of a certain data set under scrutiny. You can use it for clients pre-submission checks or also server pre-ingestion checks to do. Once that is all done, we have a shape expression within the project. We write bots that align those data regularly with Wikidata to keep the Wikidata in sync with the databases. And this is done in a continuous integration workflow, so regularly updates are being made. And then you get something like this. There is a Wikidata with its own curation cycle. And then you have a set of databases that come, or ontologies that come with their own with their own feedback loop. And then the project is trying to align between the two efforts. So for the coronaviruses, we just replicated this pipeline, going from community engagement, extracting the schema, writing the bot, and at the end of this process, we had pipelines in place, both schemas and bots for these coronaviruses, and we had the following linked schemas. So all these. We have an entity schema for diseases, for a virus strain, a virus taxon. Then we have protein, genes, pathways, and proteins and genes. And this was the end of the product. So we used the community to do that. So in conclusion and future work, we're working towards an entity schema ecosystem that aligns next to Wikidata, that helps in getting a better understanding of the relationships that are in Wikidata. Wikidata is a nice hub for collaborative work, not only on data, but also on the underlying schemas. And I would like to end with the acknowledgements of the authors, but also the GeneWiki project, the SHEX community group, and of course, the whole Wikidata community at large. That's the end of the presentation. Thank you. I think.
Well, thank you very much. That's really fascinating and interesting. Both the presentations were super cool. And we have plenty of time for discussion. We have about 20 minutes. And so maybe we can look at some audience questions, and then we can have a discussion amongst the panelists. Naren, did you want to go with some audience questions?
Sure. So we have a few audience questions. Let's start with Peter. And there's a question about Wikidata's large data size. So here's a question. One problem is Wikidata's size. For example, given its large and deep type system with nearly 2 million types. Wow, I did not know it had so many types. Making explicit all instance of relations will add a very large number of them.
So yes, if you complete the instance things, yes, you do add a lot of information. So how much? Well, really, of course, it's not for any particular entity in Wikidata. You only add the ancestors of the types that it's in already, by and large. And well, I say so for there's two things you add. You add the ancestors, and then you add the recognized ones. So that's significant. I don't think you would ever get close to 2 million for anything. You could easily get 1,000 or so, right? That would not be unusual. So yes, there is a significant pain there. However, the amount of information that's stored about every individual already is at least that much. So that let me be dismissive and say we only double at worst, right? So that's significant, but not horrible, right?
Okay, thanks. Next, we have a question for Jose and Andra. How do shape expressions compare with eMarple constraints chaining? Why would one want to use one or the other?
It seems that shape expression language and Marple that Peter talked about, their sort of objectives are the same, right? So, and then the obvious question is, okay, what's the difference?
Well, so let me say a little bit about Marple. So the constraints in Marple could be viewed as similar to SHEX constraints, right? The rule part of Marple is different. Shex generally doesn't add information to anything like Wikidata. It just checks that the things there are acceptable. But none of the details of the constraint system in actually let me modify that slightly. Wikidata already has a constraint system that looks for things like you can only have one father. Shex can do that as well, but in some sense, let me put words into the mouth of the Shex people. Shex is about creating sort of a collection of constraints that are suitable for a class, whereas the Wikidata constraints and the constraints in something like Marple are actually very localized. They are things like you can only have one parent. They are things like your children have to be younger than you are, things like that. Not essentially a complete definition of a constraint for example, the kinds of things that you want to have in human.
Okay, thank you. And
Well, so I mean, Jose, do you want to weigh in, or do you want to present your perspective?
Yeah, no, maybe another difference is that in Shape Expressions was created mainly for RDF, and in principle in Shape Expressions we don't handle qualifiers that I think in Marple it could handle qualifiers and references. Probably could be extended Shape Expressions to handle that. That would be some research.
So the other superficial expression I'm getting is that shape expression language is probably primarily for integrity checking or constraint checking, whereas Marple could be used for inference and deriving new conclusions, not just for constraint checking.
Precisely, yes.
Okay. Mm-hmm. Okay, so that's good. So next question. Why using a shape expression to validate RDF data instead of an OL2 ontology?
Yeah, that's an interesting question. I like to use the fact is, I think to me, but please Peter and Jose correct me. To me, OWL is specifically defined to describe the world, whereas shape expression is specifically designed to describe the data. To give an example, if you would use an OWL and you would say every person has 2 biological parents, which is a valid claim. If you look to data, which is in general messy, you want to describe that a biological that a person can have multiple guardians, because we are not talking about reality in life. We're talking about the data that represents the world. So you can actually, I think to me, that's the distinction between OWL and Shex.
Okay, so another way to state this might be that Shex is more sort of bottom up, like it's driven by the data, whereas OWL, it's sort of top down. You're trying to describe the world, and regardless of what the data might be.
I would make the distinction slightly differently. Shex is about the information you have, right? So Shex says, well, everybody's got to have a social security number or something's wrong. We have to have you have to be given a social security number or something is wrong. OWL just says, everybody's got a social security number. And it's perfectly fine if U of an A don't have one in our database. It's there, we just don't know it. So OWL is about the way the world is, and Shex and other kinds of constraints are about the way our data about the world is, or perhaps you could say our knowledge about the world is, although it's really data.
Yeah, I think you said it very beautifully. It's very clear, very crisp. I actually have a curiosity question for Peter. You presented this query, how many women are there in the Wikidata? Did you also pose the query, how many men are there?
I did a while ago. About the same number. No, it's the same. It's exactly the same problem. So again, to find the men in Wikidata, you have to query human for the right sex or gender, And then, of course, we have non-binary sex or gender issues. And then if you want to get adult, then you have to have some definition of what it makes to be an adult, like how old you are, right?
Yeah, I mean, that's good to know because we don't want anti-discrimination people coming after us, right?
No. All of the examples that I have given in this and similar talks is I have stumbled on without looking for them, right? I mean, if I at certain kinds, I have actually looked, but everything that I tell other people are things that I have just run into. And so this is the woman one is particularly because somebody asked me, right? And I said, well, I don't know, let me find out. And whoa, that's weird, right? And if I would give it just an anecdote about the reaction to that, the reaction I got from Wikidata people was, oh, 42 is the wrong answer, it needs to be 0. So somebody went around and got rid of all of those and essentially deleted the links between those 42 things and women, right? Actually, and subclasses of women, because their opinion was there should be zero instances of these things. Now, of course, that's a better answer, right? You could then go along and say, oh, there are these classes in Wikidata that will never have any told instances, right? You never should say that somebody is a woman. Instead, you should say that they're human with a sex or gender female and the right age. And that's the way you do it. But there's nothing that says that that's the case, right? And so, and of course, because there was nothing that said that's the case, people went along and created these individuals that ended up being instances of women.
Okay. Well, thanks for that. So I have a question for Andrea and Jose. I mean, it's interesting that you went about adding information about COVID to Wikidata. What impact has it had? I mean, has anybody made use of it? I mean, did it lead to vaccine discovery, or I mean, what's the benefit of doing it?
That's a good question. The benefit of it, well, actually, there is the paper is just out now. The benefit is we had a lot of follow-up projects. So, for example, one of the follow-up projects was modeling complexes. So I would say it's hard to say now, did we find the vaccine? I think it's safe to say no, probably not. But what it helped is it got data into other, so it created a collaborative environment between researchers who were part of this project and extended. And yes, the information is currently being used there's this tool called Scholia that models the literature of that. Well, we didn't do any structural analysis yet to make conclusions in that, other than it's being used in tools downstream of Wikidata. And I'm aware of projects that are building on top of that, of which the Complex Portal is one, the Wikipathways is one. So yes, that on that level, it is just one step to other projects, collaborative projects in the research community. With respect to, did it have an impact on the vaccine? Well, that would be nice to know, but that's really some additional research to do. But the other benefit is also, and that was our aim as well. I mean, we met because we were in lockdown everywhere in the world, so we used the COVID as the narrative to drive this protocol. So the bigger benefit is that we finally have a protocol that's being published and can be used in other use cases, whether it's shipwrecks or rivers or anything that you want to do. And that can now be used. And so yes, I think that those are the points that can be made. There is one more point that I want to make. We keep talking about constraints, and it might be a bit nitpicking, but I would actually say that shape expressions is not about constraints, but about expectations, which I think is why shape expression is so interesting. To stick to the example of Peter, when we started out in GeneWiki, put the human genes in Wikidata, we put in, it's a gene of Q5, which is a human. And at some point, we were not able to reproduce evolutionary trees based on data that was in Wikidata for the fact that we needed to model it to Homo sapiens, because those taxonomic information, that taxonomic information is not in Wikidata close to human, because it also acts to a belief system that someone doesn't believe evolution happens for humans. So we had to create a Homo sapiens item, which is parallel to human, to be able to reproduce that use case. And so there is conflicting information in there, and which is nice about shape expressions, because how do you distinguish that is that you can actually look at the references and qualifiers that are being added to the Wikidata community. So as a user, you can decide, I only want to have that subset of Wikidata that follows the following references, that following the following patterns. So, and that's, for me personally, is my the time why I invested shape expressions. Is the shape expression allows me to express that that expectations. So it's not a constraint on the data, it's an expression of my expectation. And I'm personally also still talking about constraints, but I'm trying to change that into not a constraint check, but a check for conformance to the application view or the application profile that is driven by the use case.
Okay. So yeah, I mean, you can say that, well, shape expressions are use inspired, right? How you are actually going to use that data and how you expect your application, what your application is expecting, right? So
yeah, users, but also data publishers or data owners.
Yeah. So there are a couple of comments about context. How do we organize ways of describing context, and what is context? If time and space dimensions of context. Maybe Peter, you could shed some light on this.
So, yes, and we're immediately into philosophy, right? So, right, we can now go away for 2,000 years and think about the problem and not come up with any answers. But of course, we are computer scientists, and so we need to come up with some rough and ready thing. So the qualifiers that are in Wikidata, or the attributes that are in many other knowledge graphs, you can divide them into two kinds of things. One of which gives sort of just extra things, so that aren't really contextual. Like Elizabeth Taylor married Richard Burton in wherever it was, I don't know, Las Vegas, let's say, right? So we don't generally think of that as a context. You could, if you would. Perhaps the one thing that we almost always think of as contextual is temporal extent, right? So if we have a temporal extent, that is definitely context. And other things are really, I generally don't worry about them as being context. If I wanted to, it would be things like, here's perhaps a good one. So also having to do with marriage. So suppose that we're asking a marriage question about, and we cared about what kind of marriage you were. So essentially we wanted a marriage in the context of Christianity. So we only accepted Christian religious marriages. That might be a different kind of context. But really the biggie is time, right? And you would think, oh, that's no problem. We just have end time and start time. But in Wikidata, there are quite a few qualifiers that have to do with temporal context, and they grow. I mean, I looked a few years ago and there were a couple, and I looked again and there was one or two more, and I've looked again and there was yet another one. So again, here I am, a poor computer program. Somebody has got to tell me when these things happen, and there's no way of finding that out except by a human noticing where these things are and doing some thinking, right? So, but yeah, I mean, are they metadata? Are they not? I don't like metadata as a notion at all. It's just data of one form or another.
Cool. Mike is ready to say something.
No, I fully agree with what Peter was just saying. I mean, the context notion is useful sometimes when one wants to pull some data out of the data and make it into a context, and then sometimes you want to put the data back out of the context back into the data. It's a useful mechanism, but I don't think philosophically you need to have it in one place or the other. I agree with Peter that I prefer minimum at its metadata. That's absolutely the case. I just wanted to also point out that there is one other thing in addition to time, which is beliefs. Different people believe different things, and it's a fairly common to represent that within context. Vinay's view of the world versus Mike's view of the world versus Peter's view of the world.
Yeah.
That's another thing that goes along with time as a fairly common use of context.
Yeah, I think the example that they gave earlier about some people believing in evolution versus some people not believing in evolution, that was an interesting example of beliefs, right? So.
I mean, there are assumptions too. You know, you have frictionless planes. Is there friction or not friction? You have simplifications and so forth. So there's many things you might want to use the mechanism for. And what I need to do is we need to be able to move back and forth between the use of context and putting that same amount of information directly into our data. I think Peter's right. There's not going to be an easy answer to this anytime soon.
Yeah,
and
but
we've got to move forward.
For most current knowledge graphs and the applications that they get used in for, time is really it. They don't store beliefs. They don't store frictionless stuff. They don't really have information. You know, they can't handle physics, right?
Agreement. Agreed. Time is number one.
All right. So I think that's a good place to conclude. We are at the end of our class time. So I really want to thank our speakers. I think this was really fascinating discussion. You guys stuck to time. We had a good time for discussion and good interchange. We got good understanding of what each of you are doing. So thank you all very much. And as far as the class is concerned, we'll continue next Tuesday. And next Tuesday or next week, our focus is going to be on creation of knowledge graphs from structured data. So see you all then, and bye for now.